Hello folks, today we're going to be going over the 15s. This comes up in a lab that we do. There we have a quiz on it. Also makes its way onto the test, so it's a pretty important concept. So up here we have some multiple choice questions. You can see there's 5 questions, there's 4 answers, so it means you have to use some of the answers more than once. You can take a look at the A, B, C, and D and see if you can figure it out in your head. That's awesome if you can. Otherwise, I'm going to show you how to do math in order to solve these problems. So you're going to need the cover of your unit pack because we're going to be doing some moving around from these liter islands. And we got moles of base here and moles of hydroxide. And then we might go from liters of acid to moles of acid to moles of hydrogen ion. Those are some of the things that we're going to be figuring out as we're going through these problems. So what I did is I have some math over here. It's A, B, C, and D. You have it on your sheets as well. That'll help you answer the questions, or you can look at the problem and maybe you can figure it out that way. So number 1, has the most hydroxide ion? Well, hydroxide is right there and hydroxide is right there. So I've just limited my answers down to A and B. 3 drops of 0.1 or 1 drop of 0.8, which is going to have more hydroxide ion in it? If you can see it, that's great. You can put your guess down on your paper right now, but we can look at the math of it as well. So A and B, here's the math for it. And what we do is we say 3 drops to 1 drop. As long as they're drops to drops, all is good in the world. And we could say, 3 liters of sodium hydroxide to 1 liter of sodium hydroxide. 3 gallons of sodium hydroxide to 1 gallon of sodium hydroxide. As long as you keep the measurement unit the same, the comparison can be made as long as there's 3 of this and 1 of this. So let me show you how we did the math and use the cover. We'll go through this first one. Again, 3 drops, we're going to equate to 3 liters, or 3 liters of sodium hydroxide. Liters of base are right down here at the very bottom of your mole map. From liter island, we go to moles of base. So liters of sodium hydroxide are right there. Liters of sodium hydroxide go on the bottom of that step. This spot right here is called moles of base island. So I can go to moles of sodium hydroxide. That is the base that we used here. And then moles of sodium hydroxide are on top, so they go on the bottom of the next step. And we can go up 1 more island to moles of hydroxide island. So if you take a look at that, we went from liter island up to moles of hydroxide island. And we ended up getting 0.3 moles of hydroxide. We did very similar math, followed a very similar pathway on that map. And for B, we got 0.8 moles of a hydroxide. Well, which one has the most hydroxide? That would be B, and if that was your initial guess, that was awesome. The way Mr. Brosnan and I kind of look at it is 3 drops of 0.1, that's 0.3. 1 drop of 0.8, that's 0.8. And you can look at it that way if you wish to as well. What is the most dilute base? Well, dilute and concentrated all have to do with molarity, so it's all about the molarity. Drops have nothing to do with it. This one's a 0.1 molar, this one's a 0.8 molar. Which is the most dilute? The 0.1. So the answer is A for that one. 3 has the most hydrogen ion. Well, so C and D, we have these H's out front. Those are the ones that are the acids. So which one has the most hydrogen ion in it? So we're down to C and D. Acids are up here, so this is liters of acid island. This is moles of acid island, and this is moles of hydrogen island. So it wants again to know which one has the most hydrogen ions. So I have 3 drops of C and 1 drop of D. As long as I keep the unit the same between the 2 of them, I can have 3 of anything to 1 of anything. So I went with 3 liters and 1 liter. I'm going to do C. I went from 3 liters to mole island. So 3 liters are here. Liters go down on the bottom of the next step. I can convert liters to moles according to my map. Moles of hydrochloric acid are right there, so that label has to go on the bottom of the next step. And I can go from mole island to moles of hydrogen island. And then I could solve my problem. I do the exact same thing with D. Whatever label's on top goes on the bottom of the next step. And I just follow my map like that. I do that math, and I end up getting 0.8, oops, excuse me, wrong one there. I end up getting 1.2, or if I use sig figs, 1 mole of hydrogen ion. And here I get 0.4 moles. So which one has the most hydrogen ion? That would be C. And if I look at it, 3 times 0.4, that's 1.2. 1 times 0.4, that's 0.4. I can see that right there. Again, that's a shortcut way of doing it. You will have to do the math on the next one to figure out these. Has the most moles of base? Well, if you have the most hydroxide ions, you have the most moles of base, so that's going to be B. And again, I can look at this right here and can do my comparison. And which is the most concentrated base? The 0.8 is more concentrated than 0.1, so that is a B as well. Again, this kind of math will be used throughout this unit and on the next sheet. 6, will mixing A and D be pink or colorless? Well, if I look at that math and I see that I have 0.3 moles of hydroxide and I have 0.4 moles of hydrogen ion. Hydrogen ion comes in contact with hydroxide ion, and those two make water. If I have extra hydroxide ions left over at the end and there's phenolphthalein there, it'll be pink. And if there are no hydroxide ions left over at the end and there's phenolphthalein, it'll be colorless. If I look at this whole problem, it looks like I have more hydrogen ions than hydroxide ions. So all of the hydrogen ions react with the hydroxide ions that are there and make water, making the hydroxide ions completely disappear, leaving us with some hydrogen ions at the end. And hydrogen ions and phenolphthalein are colorless. Will mixing B and C be pink or colorless, and why? So again, I look at the math. I got 0.8 moles of hydroxide ion. I have 1 mole of hydrogen ion. In this problem, I have more hydrogen ions than I have hydroxide ions. So all the hydrogen ions will react with all of the hydroxide ions until all the hydroxide ions are used up, leaving us with water and some hydrogen ions that are unreacted. Hydrogen ions and phenolphthalein do nothing, so they stay colorless. Bugs Bunny's a curious fellow who became bored while watching his favorite TV show. He happened upon 8 bottles of colorless solutions. Bugs was wondering what would happen if he mixed the different bottles of solutions. With the first mixture, nothing happened. As he mixed 2 more solutions, he got the same result. Nothing happened, or at least it appeared like nothing happened. To Bugs' surprise, however, the third mixture he made turned pink. 4 bottles contain different concentrations of base. This OH at the end lets us know that it's a hydroxide and it's a base. And then 4 different molarities of HI, which is an acid. H's on front tell us it's an acid. So the 4 bottles of acid also contain the indicator phenolphthalein that turns colorless in the presence of hydrogen ions. State colors. Phenolphthalein is colorless in acidic solutions and is colorless in neutral solutions and is pink in basic solutions. So here's the information that Bugs Bunny got. He put 3 drops, I'm on 1 right now, he put 3 drops from T1 and 5 drops of T5, and he got a pink color. That means he's got 1 that's an acid, 1 that's a base. We don't know which is which. 2, when 2 more drops of T5 were added to the pink solution, the solution turned colorless. So when he added T5, the pink color went away. So T5 is an acid, and T1 is a base. You should definitely try this yourself, see if you can do it, and then compare your answers to mine. 3, when 5 drops of T4 were added to a pink solution, the solution turned colorless. 5 drops of T4 were added to a pink solution and it went colorless. T4 must be an acid. Number 4, when 2 drops of T8 were added to 2 drops of T1, the solution was colorless. But a third drop of T1 caused the solution to turn pink. So T1 must be a base, and we already had that information, so it just confirms that. But it does tell us that T8 must be an acid. 5, a pink solution stayed pink when 20 drops of T3 were added to the pink solution. 20 drops is the most drops you'll ever add. So pink solution stayed pink when 20 drops of T3 were added to it. So if you're adding a base to a pink solution, it's going to stay pink. So T3 is a base. 6, a pink solution stayed pink when 20 drops of T6 were added to it. T6 is a base. You add base to a pink solution, it stays pink. And 7, when adding 4 drops of T2 to 2 drops of T7, it was colorless. But adding a third drop of T7, it turned pink. So T7 must be a base. And therefore, T2 must be an acid. I have 1, 2, 3, 4 acids and 4 bases. So now we've got to figure out what's going on with this scenario. So we're going to read it, and we're going to look at the data table. So Bugs wanted to figure out why it took different numbers of drops of different solutions to get a pink solution. And why adding some more of one bottle but not another caused the pink solution to become colorless. Based on the following data, what are the concentrations of the acids and bases with those molarities? Starting with the same pink mixture in 4 different wells, the following numbers of T2, 4, 5, and 8 solutions were needed to turn the solutions colorless. Write the concentrations of the solutions. So, T2, T4, T5, and T8. We know that those are acids. These are all acids. And if you have to, you go ahead and write that in there. Acids. It tells us the number of drops of these acids to go from pink to colorless. So this one took 2 drops of this acid to go from pink to colorless. And this one took 9 drops of this acid to go from pink to colorless. That tells me that this T8 must be a lot more concentrated to go from pink to colorless, because it did it in 2 drops. So I would say this is my 0.8, and my acid is HI. So this is my 0.8 molar HI. This 9 took a lot of acid. It took the most drops of acid, so it must be the most dilute. The second most drops would be the second most dilute. And then we have this one. Okay. Try it yourself. Cover it up again, see if we can figure it out, but this is kind of key to the next worksheet. B, 3 drops of T1, T3, T6, and T7 were placed in different wells on a spot plate. I look at my data and I find out that those are all bases. 1 drop of T2 was added to each of the 4 cells and turned pink. When more drops of T2 were added to each of the 4 cells until the mixture turned colorless. Identify the concentrations. So 3 drops of these guys, these are all bases. So 3 drops of each of those are placed into a cell. And then this is the number of drops of acid to turn colorless. And it's all the same acid. So this one took 24 drops of acid to turn that base from pink to colorless. And this one took 3 drops of the exact same acid to go from pink to colorless. This 3 drops, it did it in a very small amount of drops of acid to turn that from pink to colorless. So this T6 here must be very dilute. There must not be a lot of base there. So this is my 0.1 molar lithium hydroxide. So let me go over that one more time. This one took 3 drops of acid to go from pink to colorless. This one took a lot of acid to go from pink to colorless. So this one must be very concentrated, And this one must be very dilute.